Okay, hi, I'm Palmer. I run the software team at Sci5. I'm also the vice chair of the RISC-V software working group. Along with Arun and I submitted the talk, but Arun recently had a child. I think he might actually be here, but unfortunately that means you're subjected to me for the entire half-hour session. So sorry if that wasn't what you signed up for. So I thought, there's a lot of software, and it's really hard to describe the entire state of RISC-V software in even one presentation. So I thought, well, let's at least try one slide. Right? So here's kind of the demo we set up last night. So I flew out here with a computer in my backpack, a RISC-V computer, the Hi-5 Unleashed, along with the recently announced microsemi board, and a graphics card and a USB card. And I went and I downloaded from the internet the RISC-V Debian port. I installed it on an SSD. And I went and installed a bunch of packages, got X up and running, and we have a web browser, a terminal. We can use a webcam to take a picture of me, kind of. I had to take one with my phone because I don't really know how computers work. And then also we can play some 3D video games with hardware-accelerated graphics. And this has really come a long way since I started working on it. And it's at the point where RISC-V you can build a real computer with, and it feels like actually using something if you have a Linux-capable board. So like I said, we've come a long way. We'll dive into each of the individual steps. If my clicker clicks, there we go. OK, yes. So the real core of the RISC-V software ecosystem, or any ISA port, is the compiler, because that's where most of the architecture-specific work gets done. The RISC-V ports of the GNU toolchain, so binutils and GCC, which are the assembler linker, and the compiler, have been upstream for about a year now. We did a lot of this work at Berkeley, and that continued at Sci5. Additionally, glibc, which is the main C library, has also been upstream for a couple of months. And this was the point at which we could really start to drive RISC-V adoption, because that meant that the ABIs are stable and people can start using it to build real things. We also have an embedded C library called newlib, which is kind of the standard embedded C library. That's been upstream for a little longer than the glibc port, because it didn't depend on quite as much ABI stabilization. We didn't need the Linux ABI to be stable. But that's also stable, ready to go, and has been released. And we've come a long way since I started working on this. Because when I started working on it, I was at Berkeley, kind of sitting across the lab from some people working on RISC-V software, and I'd hear all the time, hey, there's a bug in this, a bug in that. And I thought, gee, that looks a little more interesting than whatever I'm working on. So I thought I'll go kind of get involved with the RISC-V software stuff. And at that point, everything was a software bug. Nothing worked. But we're at the point where if your code doesn't do what you want, it's probably not a compiler bug. And it's hard to enumerate everything that's not a compiler bug, but there's one specific one I'd like to call out. If you can't get 1.61 dmips per megahertz on the E31, it's not a compiler bug, so please stop calling. In addition to compiler, the other large piece of the Linux, software stack for RISC-V is the Linux port. Linux port deals largely with the devices and the privilege specification. Our Linux port has been upstream since early this year. It only supports RV64i-based systems right now. So if you're interested in contributing, adding RV32i support, or I guess fixing the bugs in RV32i support would be a good way to get started. Additionally, the Linux itself, the port to the core architecture exists, but there are many drivers that are necessary. We have a lot of these drivers in out-of-tree branches right now. So if someone's interested in helping out with the driver porting effort, that's something we're slowly trickling through. But the Linux port is largely functional. People are willing to take out-of-tree driver patches because they're fairly self-contained. And to announce the Linux port, Sci5 sponsored a hackathon at the Embedded Linux conference in Portland earlier this year, where we gave people access before the public release to the Hi-5 Unleashed boards, which is our quad-core Linux-capable development board. Right? And we had a little kind of programming contest. And someone ported SpiderMonkey, which is the Mozilla open source JavaScript, not the JIT part, just the interpreter. And then also we got Open Embedded up and running on the board. And you can see the winners over here. And to me, this was a really cool moment, walking through some large hotel somewhere and seeing Sci5 up there with Intel sponsoring a conference. I thought, gee, it's a really big logo. The Linux port getting upstream was really kind of a watershed event for RISC-V, because it meant people started taking us seriously in software land. Before you have a Linux port, your ABIs aren't stable, and no one really knows how far you're going to get. But once the Linux port's upstream, people think you're real. The glibc people are willing to take your port, and more importantly, the distribution people are willing to start working on it. So we've been running a beta program where we give open source developers a free development kit, which includes the Hi-5 Unleashed, and if they were really early, a Xilinx-based FPGA to do PCI Express. We've given one of these to the Fedora people, actually 2 or 3 of these to the Fedora people. And I am happy to announce they've reproduced the FPGA shells using the open source repositories. So it's all there, it kind of works. They've been booting Fedora on the board. We have an SSD that will boot up Fedora. You can download and install a bunch of packages. Kind of feels like a real computer. And there's a talk about this on Tuesday, which I think is today. I'm never really sure what day it is. Yeah, it's really tough when we change time zones. So today, yes. Additionally, we have Debian, as Kirsten mentioned. The Debian progress has been very rapid. We're up to about 80% of the packages building, which I thought was 40,000, but Kirsten said it was 10,000, so I'm probably wrong about that. They also have a talk today, and this has been a real great community effort. Both the Debian open source community has been involved, and also one of our Sci5 internal developers, one of the guys who does the memory system actually, saw that Debian was lagging in progress behind Fedora and thought, gee, we can't let that happen. So spent a bunch of time porting some packages and getting things up and running. And it's a point where we're really intercepting with the kind of major supported architectures that have been around for a long time. Things like Itanium. I guess that's a good thing. With the core of Linux distribution starting to come up, you can start to do larger software development on RISC-V. And one of the large efforts going on right now is the LLVM porting effort. So LLVM is the kind of modern compiler suite. Alex Bradbury has been leading the charge on that for the last few years, working on at the Low Risk Foundation. He had a talk yesterday at the tutorial describing the state of the RISC-V LLVM infrastructure and how to start working on that. And additionally, he has a poster tonight, so he should be around. You should be able to go talk to him. It's a really exciting project, especially as a GCC developer, I'm very excited for LLVM. Hopefully that will spin up quickly. It doesn't support all of the ISAs right now. It also doesn't support all of the calling conventions. And it's missing some of the compressed stuff and some of the linker relaxation stuff to get really high performance code generation. But there's a lot of interesting work to be done there, and hopefully that will move forward quickly. It is functional. The client port, which is the C and C++ front end, has run stuff. We also have a Go port bouncing around for it, and OpenJDK has run some code, and there's a patch available to make the interpreter only work. The Rust port, which is Mozilla's language, is in progress, and I believe there's a poster on that today. So if you're interested, and you're a compiler person, you're interested in getting involved in RISC-V software development, this is a great place to start because there's lots of work left to be done, and it's a very exciting, fast-moving project that's used by many people. Many of the 20% of packages that don't build in Debian, we're starting to reach the point where those don't build because of LLVM dependencies. So it's an important thing to get up and running. Additionally, we had a free BSD port. We've had this for actually a long time. It's been upstream since 2016. It's been talked about at a couple of RISC-V workshops. It matches the latest RISC-V privilege specification, which is a good proof that you can actually implement the privilege specification, because not only do we have a Linux port, we have a BSD port. So it is actually a good enough specification. You can implement it without sitting across the room from Andrew. It's also been demonstrated booting on some hardware implementations, which is always a good sign. A demonstration that the standard actually works. Right. In addition to having the supervisor mode code work, you need a lot of firmware for application cores. The one we currently use is the Berkeley Bootloader, which is called BBL, which came out of the research project at Berkeley, and it was really never meant to be a kind of standard commercial strength bootloader. So while it boots our cores and it's what is on the boards that we give people, it's not really what we want long term. The long-term plan is to support standard bootloaders. And there's a few different spaces in which bootloaders have become standard. U-Boot's a common one in embedded Linux land. A port of that is upstream, thanks to the Andy's team, who's done a lot of work on the compiler and also helped out with our Linux port. There's a port of that to their NX25 board, which is an RV32i board. We don't yet have support for RV64i boards or the High-Five Unleashed, but that's something we're working on. Additionally, there's a port of Tiano Core in progress, which is the open source UFI implementation. Abner Chang from HPE is doing that. He's been working on it for a while. It's an exciting thing because UFI is necessary in the server space to actually get kind of large real systems up and running. The core boot port is also upstream, and if I remember correctly, it's out of date. It's been upstream for a very long time, since 2014. One of the first pieces of RISC-V software to actually get upstream, which is part of the reason that it's out of date. And that's another bootloader that's popular. It runs on Chromebooks, I believe. The UFI standards process is also in progress. kind of sitting on some of the standards bodies, and we hope to get a proper UFI standard pushed through, so you can boot RISC-V on UFI/ACPI capable systems, which are common in the kind of larger space as opposed to the embedded Linux space. So in addition to kind of application core sized runtimes, there are a lot of important embedded runtimes. Zephyr, which is a new, or not a new, I guess a newly open sourced RTOS, is upstream. It only supports RV32, but it does run on our systems, and you can run demos, and it seems to work pretty well. The SEL4 port, which is a provably secure microkernel-based operating system, has been upstream for a couple of weeks, and that's a very exciting direction. We also have support for free RTOS, though the support's not upstream yet, and it's not quite as in good a shape as the other embedded runtimes are. So if that's something you're interested in developing on, free RTOS support's a good way to get started with RISC-V development, because there are a lot of people who are interested in it. And there are also a few commercial embedded runtimes that are interesting that I know less about because I'm a little more of an open source person. But Micrim has announced a port of their stuff to the Microsemi FPGA-based RISC-V implementations. And ThreadX also had a talk a while ago at a RISC-V workshop about their support for RISC-V. So it's good to have the software working, but it's also really important to be able to debug your software. We're no longer, when it was kind of an academic research project, we should say, yeah, sure, we write software without bugs, but that just means no one uses it, right? So now that people actually use this stuff, there's bugs and you have to fix them. The RISC-V external debug specification is what's being used there. So that is a JTAG debug specification. You can use external debuggers. It's meant to be portable across both implementations and software vendors. Megan's running the task group at Sci-Fi. We have an OpenOCD port for that, which is a little bit hairy, but we're working on making better. Hopefully we'll get that upstream over the next few months after it's in a little bit better shape. There's GDB support for that as well, which is not directly related to the external debug support, but you can have a full stack embedded debugging flow on RISC-V right now using the standard open source tools. And we're also getting a lot of commercial adoption in the debug space. I know Seger and Lauterbach have RISC-V support, and they've announced that, and they are giving talks and posters and that sort of stuff today. On the hardware side, UltraSoC supports a bunch of different RISC-V core vendors with a standard debugging framework. And IAR put up some stuff saying that they're going to support RISC-V, but I don't know the timeline on that. So this whole software development effort is really a proof that open standards work. RISC-V was designed to be the open ISA standard, and it's really started to take off. And as you can tell, the core software ecosystem, GCC, glibc, binutils, newlib, has been maintained by a consortium of RISC-V vendors. So it's not just us at Sci-Fi doing it. We'd like to thank all of the other RISC-V, the people in the RISC-V organization, including BlueSpec. Darius helped a lot fixing bugs in the glibc port. We were very close to missing the deadline, and it was very important to get it in, so that helped a lot. Andy's Keto has done a lot of work on GCC, our GCC port for years, which has been really great. We never would have had GCC in as good of a shape as it was for the first upstreaming round unless Keto had found the time to help out. And then we also have some people from Red Hat who've been contributing to the glibc port, which helps a lot. So this is really good proof that open standards actually do work and the ISA is functioning as designed. And in addition to having an open a standard for the software stack, you have a standard for implementations. Ours is the Hi5 Unleashed. I've mentioned this a couple times because I think it's pretty exciting. So it's a quad-core Linux-capable development board from Sci-Fi that you can actually go buy on the internet, unless we're sold out again. But you can pay for one at least. Right? It has DDR4. It's a real capable system, gigabit Ethernet, some SPI flash, some storage. And then an interesting part is that it has expansion via an FMC connector. So you can plug it into a motherboard to get PCI Express support, more storage, and then interesting I/O things attached to an FPGA that you can do. There'll be more of this at Yunsub's talk, which I think is later today. In addition to hardware implementations, we have software implementations. We have Spike, which is designed to be a simple RISC-V software implementation. The goal is that it's the golden model for the ISA, so it doesn't do complicated things like jitting or support a large number of devices. It's designed to be easy to demonstrate that it is correct. Additionally, we have RV8, which was done as sort of a research project by Michael Clark, who we later picked up to work on our QEMU port, which is an extremely fast RISC-V JIT. It can run at speeds approaching half of native x86 code execution on a large Intel machine, which is an exciting direction. Renode, coming from the Antmicro guys, is an IoT-focused simulation system. And then the big one is QEMU. So QEMU is the large, kind of standard open-source simulator. It supports many platforms and supports many devices on all of those platforms and supports lots of boards. And recently, our QEMU port landed upstream. Maybe a week ago, it was actually released from upstream. And it's at the point where you can simulate the Sci-Fi hardware in software and have portability between all of our different designs, which is great for software developers. And this has really allowed people to start developing RISC-V software. I know, for example, the Debian packages are all built on QEMU instances because it's faster than any available RISC-V board right now. So in addition to open source simulators, there are commercial simulators, which I'm particularly excited about because I have a rule where I won't use a programming language unless there's an open standard for it and an open source implementation for it, and then also a commercial implementation, which I don't tend to use, but it's nice to know that at least there's enough manpower there that someone can pay for it. And in Paris recently announced their commercial simulators open, which is nice because it means I can kind of actually use RISC-V now, as opposed to before. And then Esperanto also has a fast jitting simulator that they've talked about at a RISC-V workshop. And we hope that the availability of an ISA standard will allow lots of commercial development to happen. So kind of what's next for RISC-V software? You mentioned some projects and some small things to do in them, but there's a long way to go. So if you look at Linux distributions, last year I thought, OK, 2018 we'll spend the whole thing doing Linux distributions, and it's now only May, and most of the packages on Debian builds. It looks like we're going a little too fast for that to be the next thing in RISC-V software land. That's kind of the previous thing. But we're still at a point where we don't really have a lot of developers working on this stuff. So if you go and look at our Linux port, we have 22 people who have committed to it as of a couple of days ago, as opposed to 1,000 or close to 2,000 for the larger ISAs. So we still need to find some way to get developers on board with RISC-V systems. Now, some of that will be making sure that there are more hardware platforms available to develop on, and some of it's also fixing things that we lack in the software stack. Some of that are kind of important long-term projects, something like a high-performance Java implementation for RISC-V, which will be important to run large code bases in the future. There's a patch now for the Zero interpreter, which is OpenJDK, so it's the real Java. It's just quite slow. And we need a higher performance run to actually be able to run in kind of real complicated workloads. There's a working group to design the J extension. The J extension's for JITs. That's spun up now. It's run by Martin Moss, who's from Berkeley. And Boris, who has done an OpenJ9 port to other architectures, is here today with a poster, I believe, talking about his support for RISC-V in OpenJ9, which I'm very excited about, because it'd be really good to have a Java implementation. Another important thing to have are embedded runtimes, which is something we're lacking right now. I know Kirsta mentioned that we've been focusing a lot on the Linux software stack, and a lot of that's because there are higher latencies there. It takes months to get the ABI stable in Linux land and get distributions spun up, start to have packages available where you can actually do real development. You can get a little bit faster of a turnaround in embedded land, and as a result, we've been kind of not working ahead. We've been working a little bit behind. And one important thing is to support standard runtimes like Arduino. So for example, we have the Hi-5 1 board, which we announced maybe about 2 years ago, which is mechanically and electrically compatible with an Arduino, and has a port of the Arduino software stack available for it. But it's not in as good a shape as most commercially available Arduino boards. So for example, I recently came into possession of some plants that are dying because I'm bad at watering plants. And so my girlfriend comes home and says, OK, well, someone gave me this little water probe thing to plug in, but we need an Arduino, and I heard you do that sort of stuff, right? So I thought, oh, geez, I'll go look at it, right? And it turns out that, yeah, we really do need better support for Arduino. So hopefully that will come up over the next year. I think there's a lot of interesting work to be done there if you're an embedded developer who likes working on libraries and tools, bringing up support for the embedded RISC-V ecosystem, which has been a little bit slower. One exciting part of the embedded RISC-V ecosystem is that we now have some support in Platform I/O, which is a cool new, or not that new, but a cool new-to-me system that abstracts between IDEs and embedded software frameworks, The idea being that if you want to work in Eclipse and I want to work on the command line, we can all use the platform.io shim layer and work together. And then we can go retarget our project, in addition to multiple software development environments, to multiple cores and different frameworks. So if you want to use our Arduino with the actual AVR stuff on it, and I want to use a Hi5 one, you can just switch a box and target different things, and you can target multiple of them at the same time. It has support for developing via the web, so you can go online and develop on the internet, debug both remotely and locally. So you can have a machine sitting, an embedded machine attached to a Linux-capable computer somewhere, sitting off in a build farm, and then develop it from either a web IDE and debug it, or develop it locally on your system and debug via the command line. So when I saw this, I thought, gee, this is really kind of the future of embedded software development. So we're going to work on this a lot over the next few months to a year, and try to get good support for RISC-V in this, and hopefully we'll see interesting things going on there. And one more kind of important long-term development in the RISC-V ecosystem is going to be the RISC-V platform specification working group. So right now we have a lot of ISA specifications, but we don't have a specification for the platform, which includes all the things like the devices and ways to determine memory maps and that sort of stuff. And a lot of software, particularly in the embedded space, is written towards a platform more than it's written to an ISA. And that's the reason that you lack portability across implementations for different vendors, because they're really different platforms. So the goal of the RISC-V platform specification working group is to design a RISC-V platform specification which defines profiles for various different sorts of RISC-V systems. This should scale all the way from bare metal embedded development to kind of what I call portable Linux systems, things you might see on servers that dynamically enumerate hardware, and sort of everything in between. And we're hoping that this helps drive a lot of adoption in the RISC-V space, because portability is important, particularly for software, because it's hard to target all of the available boards. This has been a thing we've kind of been talking about for a while, but it's time to really do this seriously. So it's something I hope will spin up over the next few months. We're looking for a chair. I vice chair the software working group, which is great because you don't have to do any real work. So hopefully someone will sign up to chair the RISC-V platform specification. Great, and I think, oh yes, this is the last slide that I always have. How to get involved, because this is the most important part. I give these talks because I want people to get involved with the RISC-V software ecosystem. So we're at a point where it's gotten a lot easier to get involved, because the vast majority of our ports are upstream. So if you're already, say, an LLVM developer, you're seeing our patches on the mailing lists and the patch submission and regression systems. And you can just get involved like you get involved with any other port. There's no special magic anymore. We still have our kind of legacy systems, the GitHub for RISC-V, where we keep ports that are in progress and have not been submitted upstream yet. And then we have a few mailing lists. We have a software development mailing list, which is a good place to get started if you don't see a port already available for your favorite project or whatever you want to work on. There's also a patches mailing list, which is good if you distribute RISC-V software. We try to mail all of the patches, backports, bug fixes, performance improvements, that sort of stuff, to one mailing list so people can collect it. The distribution people like to be on this. That helps. We also have an IRC channel, which is fairly active, and I hang out in there sometimes and we talk about stuff. It's a good way to, if you have some interesting thing and you want a quick response, you can go chat about it. The RISC-V Linux port has its own mailing list. I think it's the first one of our ports to be spun off into a mailing list. It's not very high traffic like many of the other kernel mailing lists, so it's a good way to get started if you're interested in doing kernel development, but you can't take the 5,000 emails a day. There are a few projects that are kind of interesting to get started on if you're looking to do something. One of them would be RV32i support in both Linux and glibc. We have most of the code there, but there's some bugs that need to be fixed, and be a good way to get started doing RISC-V development, learn some of the vagaries of defining an ABI and that sort of stuff. Additionally, we have some things that are lacking RV64i support. Some of these things are in the embedded space, like Zephyr and FreeRTOS, and then some of them are in the Linux-capable space, like U-boot, which we would need to boot on our cores. Another way to start to help is to help out with the RISC-V platform specification, either to get involved talking on the mailing lists, or to join if you're a member of the RISC-V Foundation when the platform specification spins up. And one thing I'd like to announce, or I'd like to make sure everybody knows about, it's been going on for a while, is the beta program we have for open source developers. So if you are an open source developer and you have some project that you'd like to port to RISC-V, and it's kind of a large, interesting project that would be helped by the availability of RISC-V hardware implementations, we'll try to find a way to get you a board, either an FPGA-based board, or now more likely one of our Hi5 Unleashed boards. so you can do your development. Also, we have available the embedded FPGAs and the high-five ones. Those are a little cheaper, so people are OK buying those. But if you want one of those, we can try to find you one of those too. OK, and I think that is my entire talk. Yeah, good.